is Julie Mullins with Stereophile and Analog Planet, and I am here with Luke from Wilson Benesch, a long-standing family-owned British company. It's been around since the 80s, and Luke is here to tell us about the US debut of the Primaridian turntable system. And this is very high-tech, involves a lot of very exotic materials and parts and engineering behind it. So let's go ahead and start with it's a suspension with the 4 pneumatic, they're electronically controlled with microprocessors inside, just automatically to a very fine level, yes?
Yeah. Thank you, Julie. And it's great to be joined by Stereophile here. We're here courtesy this year of our new importer, Fidelity Imports. And we're joined in this room by AudioFlight as well. But yeah, you're right. This is the US debut of our turntable technologies. So what we actually have here is the Primaridian. It's the second model down in what is now our GMT collection. And the first model in that was the GMT1 system, which is the pneumatically suspended system that you mentioned. What we have here is the Primaridian. So principally the difference between the GMT and the Primaridian is that this is a suspended system using suspension, so springs, and the other one is a pneumatic suspension. So that has 4 rams in each corner, and it's driven by a compressed air system, basically. It's the same compressed air system that you use in electron microscopes, where you're trying to get a perfectly stable and a platform that basically is inert from any energy that's coming from the external environment, so anything from Earth or anything like that. So no resonant frequency can get through to the tonearm and then the cartridge, of course.
Nothing direct or indirect, it also works to a very micro level as well, right?
Yeah, so it's microprocessor controlled, so if it goes out of level, it corrects within milliseconds. But in terms of isolation, it's I think 1.8 hertz vertically and around 3 hertz horizontal. So
that's quite remarkable, yes.
Yes, it is.
Very fine specs. Yeah, well, let's go ahead and talk about the tone arm too, which is very exotic looking. This is the Graviton tone arm, and it is 3D printed with very sophisticated engineering, and it also has such an organic look and feel to it. And it's built layer by layer. You were describing welding liquid metal with a laser, just building the layers. So can you say more about that?
Well, yeah, something you hit upon there. You said it has an organic form. We say really that if nature were to grow a tone arm, this is what it would look like. And it's not a disposable comment. We mean that. And why we say that is because with additive manufacturing, what you're able to do is you're able to create structures that previously would have been impossible using something like CNC technologies. We do still use CNC machining within our factory. It's very useful, but when you're trying to do something like a tone arm, where you have a very, very specific job of that component, you don't want lots of material redundancy. In fact, you want 0 material redundancy. And by that, what I mean is there should not be anything in the tone arm that shouldn't be there. So whilst this structure is made from titanium, which is a metal, all of this counterbalance structure here is actually hollow in some parts. So there are the tessellated structures that you see here at the back. The reason why we have added those there is because you need this structure to be able to link to the counterbalance at the back of the structure. But what you want there is minimum mass, because it is above the pivot point. So you're wanting to lower the center of gravity of the tone arm as much as possible. So we add this tessellated structure here so that we're reducing any material use there to the absolute minimum.
And yes, and also you can adjust a VTA at a very micro level as well with a remote control, no less, isn't that
That's absolutely correct.
And
so just like we discussed with the systems for controlling the level and using electron microscope technology, with the tone arm, where you're trying to set a VTA position so that you can measure a groove in a piece of vinyl, which is nanometers. We're now realizing that the data within these grooves is actually down at nanometer level. You need high precision systems. So the position of the tone arm in terms of the angle is controlled via piezo device. So we have the shaft here, which has got, it's like having 4 or more legs that walk and also simultaneously hold the shaft at the same time. So you're kind of pushing and moving it along, but it's never in free space, like with a thread or something like that. You turn it and it might have a bit of recoil. This is being permanently held whilst also being moved. If you look at YouTube and just type piezo device, it's fascinating. But they use this for tracking distant stars. So if you're trying to track a star with a telescope from Earth that's billions of light years away, you can imagine that there's smallest discrepancies within that movement from the piezo device will mean you're billions of light years away from where you want to look. So you use piezo devices for that, and we've employed that technology here.
And one other comment on the back, also the counterweights are kidney-shaped, another organic element, and they contain titanium powder as well. Why did you go that route?
Well, if you are growing something from a bed of powdered titanium using lasers and you're building it step by step, you can really do anything you want. So you can choose to remove the powdered titanium as you're growing it, and it goes across like a screen like this. Or if you think that it can be useful, like for example in a tonearm where you're trying to manage resonant energy in the structure and eliminate it as much as possible, you can see why adding a powder into a solid structure would be useful, because it's like having a sandbag, effectively. Of course, they're not heavy, but the powder acts in a similar way to what we've got in these elements here, where we've got fractal damping, you call it. It's where you've got lots of different particles of different sizes, and when you get energy into that structure, each one resonates a small amount, and they each rub against one another and generate heat. So you're dissipating resonant energy, structural born resonance, as heat.
That's
we're doing the same thing here. It's called fractal damping.
Yeah, remarkable. And then the cartridge you make as well. That's the Tesla cartridge in 3 versions, 3 different metals. Do you want to say a little about that?
Again, it's a titanium structure, so all additively manufactured. You can see we've got this tessellated structure, just as you can see at the back of the tonearm here. And what we've done here is we've basically created it's a body for the tonearm, for the cartridge, that is semi-open. So if you were to look underneath and from the side, you see that there's a lot of space around the generator and around the cantilever. And the reason we did that is because when we first made cartridges back in the early 2000s and late 90s, we realized that when you add a structure around the cantilever, when that cantilever is tracking the record, it's resonating. It creates energy within that cavity. And if you put a structure around it, it actually acts like a microphone. It's echoing and then picking up that resonant energy in the chamber. So we keep it as a semi-open structure for that reason. And the other one thing I want to mention here is that if you look at the cantilever, it's never been done before, but it's very simple. If you imagine you've got a cantilever like that, it's going to bend in the middle like a straw would. So we actually add
point, or
exactly. So the first thing it'll do is it'll resonate like that, and then it starts to go like that in the middle. So we actually add a tiny UD carbon sleeve onto it.
Oh.
Extremely lightweight, so it adds a tiny little bit of mass, but it adds a lot of stiffness, but also damping. So
okay. Oh, very, very ingenious. Yeah. All right.
Never been done before. Very simple.
I don't
but
think
it's
I've
never
ever
been done
heard of
before.
that
So,
either.
and we make a boron, a sapphire, and a diamond.
Yeah. And finally, just in brief, this is a very complex system with magnets and coils involved, and obviously very massive. But can you speak a little about the?
So this is the Omega drive. It is a direct drive technology, and it's fundamentally it's the core of this system. We have developed this from the ground up. We did 2 grant projects on it with funding from the British government. And how it differs from any other direct drive motor is that when you're developing a motor, what you really want in terms of a common motor is you want efficiency. So you have the coil and the magnet quite close to one another. But the problem with that is you get an issue called cogging, which is where you have an an exchange between the coil and the magnet, and so the magnet, each time it goes past a coil, it will do this kind of thing.
There's a little catch.
So you don't want that within a motor where you're trying to get speed consistency. So within this motor, you'll see there's no cogging at all. It just moves around freely. And the only thing actually that's stopping that is the viscosity of the oil in the bearing, and you'll see it just recoil slightly. That's the oil that's pulling it back. But yeah, so it's 21 coils, 14 magnets, and you'd never make a motor this way unless you were doing one thing and one thing only, which is
Purpose-built.
play a piece of vinyl with absolute speed consistency. And
Wow.
you'll actually see when I start this now, you can't start the motor in a normal way. You have to have a power supply with an algorithm in it that basically kick-starts the motor. So it adds a pulse and another pulse, and then once it starts to move and gets up to speed, it locks into synchronicity. And after that point, it's perfectly stable. There's no variation, no wow, no flutter. So when I press this here, you'll see kick, kick, and then it'll start to speed up and go up to 33 hertz per revolution per minute.
All right, and now we have the Omnium speaker. This is the second from your top of the line. Speaker and 2 cabinets. Again, extensive and innovative use of carbon fiber, of which your company, family's company, has pioneered, as I understand, since the very early 90s.
That's correct, yes. So I think Wilson Benesch is now synonymous with the term carbon fiber composites. You're correct that we pioneered the use of carbon composite panels initially in our first loudspeaker, but then subsequently the actual monocoque. So a monocoque is a single structure where you've got 2 panels in this instance and a back that joins them. So that was 1993, and I mean, bearing in mind McLaren had only really won the world championship with the first carbon fiber monocoque 6-7 years before that. It's kind of remarkable that we were making loudspeakers at that time from this technology.
All right, that kind of material in a very premium, high-end race cars, top of the line, pushing the limits of what's possible. So, and these are in two cabinets, 2 structures, and we've got 2 tandem mid-bass drivers, and then the isobaric woofers, and these are inverted. Can you talk about that?
Yeah, so we developed all of our own drive units, including the tweeters as well. So with the isobaric, it's not a Wilson Benesch invention. It's actually a French engineer who came up with this idea, but essentially we returned to it. No one else was doing it, and it's not easy to implement because you've got essentially 2 drive units in a push-pull formation. And to achieve that within a loudspeaker, you have to create a number of structures around it to mount it onto the baffle. Of course, it has to be serviceable as well. But the key advantages of the isobaric is that instead of relying on one large woofer where you've got 1 magnet, essentially, what we do is we have 2 magnets, very powerful rare earth magnets, with 2 diaphragms that are facing one another. So when one is pushing, the other one is pulling, and then vice versa. So the nice thing about that is you've got 2 points of power, so you've got lots of control. So push, pull, it's like having 4-wheel drive as opposed to 2. But what you also have is lower moving mass. So power, low moving mass equals speed, dynamics. The key thing about a loudspeaker is that you're trying to create the sense of a live performance. And when you listen to a band perform live, singer sings, drummer strikes a drum, there's no delay. It happens right there in front of you. But with a loudspeaker, you're basically trying to create this sense that there's something happening live before you. But if there's any delay between what's happening with the bass woofer, which is slow normally, and the mid-range, which is only having to move a small amount by comparison, the whole sense that you're listening to something of like a live performance, for example, as though they were there before you, is gone because there's a delay.
That time alignment piece.
Time alignment is
critical,
and that is really the core of our philosophy. So that's why we do this with the bass woofer. The step response actually of the bass woofer is equal to or superior than the mid-range.
Excellent, yeah. And there's, I see what looks like a silk dome tweeter, but it also is a composite or a special material blended with carbon fiber once again. So the advantages there, of course, are maybe preventing breakup modes, or say more about that. Less sibilance.
Exactly what you say there. It is a composite structure. So much like what we're doing with carbon composites, you're adding a stiff material in the instance with the enclosure where you've got two skins of very stiff material with a damping core in the middle. So something that is absorbing energy. What we're doing here is we're using one material, silk, which has got a really nice kind of natural character. It's not stiff.
So smooth, as they say.
Yeah, you don't get all of this kind of sibilance, which is basically the structure itself becoming excited and then having a resonant frequency of its own. So we like silk, but it will only go to around 18, 19 kilohertz before it cannot maintain the pistonic output of the diaphragm. So at that point, you have a roll-off in the tweeter. So what we did was we added carbon composites to it. Composites? We added a carbon fiber structure. So we have a ring, like a halo, around the base of the tweeter. And then across the center, in a half halo-like structure, you have another piece of carbon fiber. And what that basically does is it allows the tweeter to get through that first point at which it can no longer maintain output, and it's flat up to around 30 kilohertz.
Wow, that is quite an extension.
Yeah. So it's like a wide bandwidth technology without using metal dome.
Yeah, or super tweeter or something, but it gets into that, certainly that range of extensions. Yeah. Nice. And finally, I wanted to ask you quickly about these very special geometries. It looks like looks like a waveguide here around the tweeter, but then also in these mid-range drivers.
That's right.
So yeah, tell me a little about that.
So this is the Tactic 3.0. It's our fourth generation of drive unit. And a little bit like what we've done with the turntable, we have used additive manufacturing to evolve our drive technology into the next generation. So people would conventionally call this a dust cap, which is kind of a bit of a throwaway term for something which is actually quite important to what the drive unit's behavior is, at least in terms of its mechanical behavior. So a drive unit will have breakup modes. The structure of the diaphragm at some point will hit a resonant frequency, and that's why you have a crossover, and in quite complex designs where you've got lots of breakup modes within quite stiff drive units, you have quite complex crossovers, so they have notch filters to basically stop that when it starts to resonate. In here, first thing that we do is we use isotactic polypropylene. So it's a material in the drive unit which is quite stiff. It's a woven structure. And the advantage of that is it's got enough stiffness to maintain a pistonic output, but it also doesn't have these complex breakup modes within the structure itself. So that's the first advantage of using that material. But what we also add is this dust cap, or Fibonacci element, as we call it.
The pattern there.
That's right. And it's an additively manufactured structure. So we can define within that structure exactly where we want stiffness and exactly where we would like more compliance. So in the surround here, it's a little bit more compliant, which means that you're able to join that to the diaphragm, and when there is a breakup mode, it is absorbing some of that energy. It's creating a composite structure. So the advantage here is that within all the floor standards within this product line, the Fibonacci series, the mid-range drive unit is directly amplifier coupled because of the fact that we can look after the drive unit and make sure it's not breaking up and making a distortion within the listening.
Yeah, it's behaving properly. And,
so if you've got really nice amps, like a valve amp, for example, sounds really sweet.
Wonderful, yeah. And of course the golden ratio and then the product line name, Fibonacci. So
correct.
Great, excellent. Well, thanks, Luke.
Thank you, Julie. Thank you.